Welcome to The Explainer. Today we're diving straight into a fantastic historical detective story. We're putting ancient history under the microscope to unravel a huge mystery involving the raw ingredients of human progress: steam, steel, mathematics, and economics. We're asking a question that could literally turn the traditional timeline of human history completely upside down.
Okay, let's dive into this because it is a massive what if. Did ancient civilizations actually possess the technology to kickstart the Industrial Revolution 2,000 years early? We usually view history as this straight, upward line of progress that somehow just naturally culminates in the 18th century. But what if the ancient Greeks or ancient Indians had all the puzzle pieces, mechanical gears, steam power, advanced metallurgy, sitting right there on the table? Why didn't they put the puzzle together?
Section 1. The ancient tech illusion and the debate around Archimedes' steam cannon. To figure this all out, we kind of have to start with the heavily debated legends surrounding the Greek genius, Archimedes. Could his defensive war machines have actually crossed over into industrial-era steam power? Well, Italian engineer Cesare Rossi proposes a truly fascinating theory here. He suggests Archimedes didn't just use mirrors to burn ships directly. Instead, he calculates that those mirrors could have heated a steam cannon. The idea is they'd utilize pressurized steam to fire a 6-kilogram clay ball completely filled with incendiary fluid at a staggering 60 meters per second.
Honestly, it's an incredible mental image, but we do have to weigh this theoretical physics against hard historical reality. Rossi's brilliant solar steam theory is absolutely mathematically plausible. However, it hits a massive wall of deep skepticism from historians of ancient technology. The glaring issue? There isn't a single historical source from Archimedes' own time that actually mentions a steam cannon. The earliest mentions come from medieval and Renaissance writers, which is centuries after cannons were already invented.
And this brings us to a really foundational concept in understanding ancient technology. As expert Tracy Rail notes, Archimedes' name attracts inventions to itself like moths to a flame. Historians view the steam cannon not as a genuine ancient artifact, but as a medieval projection. Because Archimedes was this quasi-mythical icon of invention, later generations just sort of incorrectly assumed he must have invented their modern weapons too.
Let's move to Section 2, Real Mastery with Indian Bronzes. So if Greek steam cannons are a myth, we need to shift our focus to undeniable archaeological proof. And this perfectly illustrates our point. Traveling over to ancient India, we find things like the first millennium BC Nilgiri high-10 bronze bowls. This isn't just an old cup, it is an absolute masterpiece of material science. Documented extensively by researcher Sharda Srinivasan, these megalithic artifacts are incredibly thin, sometimes just 0.2 millimeters thick. They display a level of metallurgical control that was virtually unmatched in the ancient world. Let's unpack the actual science behind it, because it's brilliant. These artisans were working with binary high-tin beta bronze. Normally, adding a lot of tin makes copper incredibly brittle, but these ancient metallurgists discovered that by using precisely 22 to 25% tin, followed by a rigorous cycle of hot forging and high-temperature quenching, they could freeze the molecular structure into a beta phase. The result? A bronze that boasts incredible tensile strength, rings like a bell, and polishes to a brilliant gold. Remarkably, chemical tracing suggests this tradition dates all the way back to the Harappan civilization around 2000 BC. And the craziest part is that this isn't just lost ancient history, it's a surviving chain of knowledge. Ancient artisans realized that pushing the recipe up to 33% tin created delta bronze. At that point, it becomes brittle like glass, but it takes on perfect specular reflective properties, making it ideal for mirrors. This continuous, unbroken chain of highly advanced industrial specialization actually survives today in Kerala with modern Aranamulla mirror makers. Which brings us to Section 3, Math meets the cannonball. Okay, so we have the materials and we have the skilled labor. But to build a revolution, you need a calculated blueprint. How exactly does a civilization go from forging a beautiful golden ball to calculating the pressure and trajectory of a heavy industrial machine? For that, we have to leap forward to 16th century Venice to meet Niccolò Tartaglia. Known as a maestro d'abacco or abacus master, Tartaglia achieved historical fame by finally formalizing the math needed to understand projectile trajectories. He essentially looked at the sheer chaos of a firing cannon and tamed it with numbers. Tartaglia's methodology back in 1537 was totally distinct. First, he used physical reasoning to observe the motion. Second, he applied traditional Archimedean geometry to map the space. And third, and this is the most crucial part, he integrated algebraic calculation. By combining these three distinct disciplines, Tartaglia managed to take the rapid, blurry flight of a cannonball and render it into a single, predictable, calculable entity.
So the absolutely crucial point here is this. Why didn't Archimedes calculate the output of a steam engine? Well, it comes down to a missing algebraic link. The ancient Greeks, for all their undeniable brilliance in geometry, simply lacked algebra. They had no framework to separate abstract mathematical formulas from physical geometric shapes. Algebra wouldn't actually be formalized until the 8th century by a Persian scholar. Without it, the complex physics required for a true industrial revolution were quite literally mathematically impossible to map out.
That leads us perfectly into Section 4, the missing industrial revolution.
We've seen that the ancients had the raw materials, localized sparks of genius, and even rudimentary steam toys, so why no factories? It ultimately comes down to a few massive societal roadblocks. First, as we just discussed, the lack of advanced algebra. Second, a heavy reliance on slave labor. Third, the lack of an inductive scientific method. They heavily preferred philosophy over experimental evidence. And finally, their economy was fundamentally agricultural. It was controlled by a small elite with basically zero mass consumer base.
Let's really drill down into that second point, though. Slaves versus machines. The fundamental drive behind the 18th century British Industrial Revolution was saving labor costs to mass-produce goods. But in ancient Greece or Rome, the entire economy was built on enslaved humans. Think about it. If you're an elite landowner with a massive enslaved workforce, you have absolutely zero financial incentive to spend a fortune developing complex, unproven machinery. You already possess the ultimate time-saving device, forced human labor. As one historical analysis perfectly summarizes regarding the British Industrial Revolution, the science to understand them and the economic need drove the invention, not the other way around. A spinning steam toy in ancient Greece was just that, a neat novelty. True revolutions don't happen just because someone builds a cool gadget. They ignite when intense economic desperation finally meets a formalized system of scientific rationalism. Which leaves us to ponder, as we witness incredibly rapid advancements today, from AI to space travel, how much of our current technology is actually driven by true societal need, and how much is just pure scientific genius searching for a problem to solve. The history of ancient steam and Indian bronze proves that human brilliance is scattered throughout all of time, but it clearly takes the perfect recipe of economics, mathematics, and raw necessity to truly spark a revolution. Thank you so much for joining me on this explainer, and I'll catch you next time.